hello everyone, thank you for joining us. I'm very excited to talk to you about mobile phase selection in HPLC and UHPLC. And I, as always, have many slides to cover, many topics that are hopefully of interest to you. Just having a quick look at the agenda, we're going to really separate the presentation up into 3 sections. The first one is looking at the solvents, the properties of our solvents, how they affect the separation within our HPLC and UHPLC methods. I'm going to do a small section on isocratic versus gradient because we've got these 2 different options available, so how do we choose? And then the final part really is looking at additives and buffers, and specifically at pH, because you've got your organic solvent part of your mobile phase, but also another powerful part of your mobile phase is that additive, that change of pH using a buffer. So we're going to look at those 3 main aspects today. Now, if we go back to the chromatography workflow, you can see mobile phase is a very key component in our HPLC or our UHPLC or even LCMS separation. And choosing the correct mobile phase and maintaining that consistent mobile phase throughout the run can really give you some great results. If you don't maintain the correct concentrations, then you can have very poor chromatography, you can get poor reproducibility, and you can get, well, a lot of downtime and a lot of investigation. So whether you're coming from a method development background or you're looking at this as QC, QA, then I think there's something in here that should be relevant to everyone. So we're going to go back to basics, as it says in the title. We're going to start with what are our solvents, or what am I talking about when I'm mentioning mobile phase? How does it fit into the separation? And then dive a little bit deeper into the choices we make and why potentially we choose one solvent over another solvent. So if we think about our chromatography, our liquid chromatography specifically, we have the mobile phase, which is the liquid moving through our chromatography system. So this is the part that moves, it carries your analytes through the whole workflow, as you can see on the screen. And if you were present at my last webinar, you will have been familiar with this sort of graphic of how chromatography works, and specifically reverse phase chromatography. So most of what we're going to talk about today concentrates on reverse phase. And in reverse phase, we have a non-polar stationary phase. So something like a fatty C18, silica with C18 on the surface. That's your column. And then we have a more polar mobile phase. And this is often highly aqueous, has a high percentage of water. So this mobile phase is really what we're talking about today, and it has some massive impacts on your chromatography. It helps to change this equilibrium of where my analyte wants to be. So the mobile phase component can change the elution order of your peaks, the shape of your peaks, and many other factors in your chromatography, like back pressure, for example. So it's very important to consider this mobile phase component. We need to think about a few parameters in our chromatogram, and most of us, we're trying to separate out more than one peak. So the main aim of our separation of our HPLC is to pull these peaks apart. So we need to think about the retention of our compound. It needs to stay on the column for a certain amount of time, needs to be retained. We need to think about how efficient our peaks are, so how sharp and narrow they are. And we also need to think about this term alpha, which is selectivity. And that is your separation factor, your separation selectivity between two peaks. We also need to think about resolution, and all the way through this presentation you'll see resolution is changed, is affected by our mobile phase. And that's because mobile phase has an influence on each of the three parameters shown here that affect resolution. So the efficiency, the selectivity, and the retention are all potentially changed by our mobile phase. So if we change the mobile phase, we will change the resolution between our peaks. We will change where these peaks come out and how far apart they are. So if we don't have a consistent mobile phase, you can see our peaks could be moving around. And that is not good for QC work. It's not good for the same method each day. It's not even good for our method development, because we want to get the same result each time when we're running the same method. So consistency is a key factor. So as I mentioned, the choice of mobile phase, and by that I mean the solvents, the additives, the buffers, these can influence retention, selectivity, and efficiency within your HPLC or UHPLC method. And probably the most simple way to look at this and think about this initially is with an Isocratic method. So what we have here is we choose a mobile phase that has a certain percentage of organic solvent and a certain percentage water, and we plot the retention time for our compounds. So if we have a look at this graph, in our method we have three peaks, we have three analytes of interest, 1, 2 and 3, and they're all represented here in different colours. Along the x-axis we have percentage organic, and up the y-axis we have the log of the retention, log of K. So what you can see immediately from this is there is a linear relationship between the percentage organic and the retention time of our compounds. That means if I change how much acetonitrile is in my mobile phase, I will change the time at which my peak elutes from the column. And you can see they're all downward slopes, which shows the higher the percentage organic, the shorter the retention time. And when I was doing chromatography, I always thought of this the other way around. So I'd think if I add more water in reverse phase, I have longer retention times. And that's because water is the weaker solvent, and our organic solvent is the strong solvent. You can also notice something else. The slopes of each of these analytes is different, and you even get some crossover here. So that means that we're changing the elution order of our peaks as we change the percentage organic. So for example, if I chose to do my first experiment at say 90% organic, so 90% organic here, my peaks would elute in order 3, 2, 1, with quite a big gap between peaks 3 and peaks 2. If I then chose to change the percentage organic to 20%, now I've got much shorter retention time for all of my analytes, and actually now they elute 1, 3, 2. So my peaks have actually switched around. And this linear relationship is actually something we can use to choose which mobile phase to work at if we want to run an isocratic method. and we've got good peak tracking. It's also what a lot of the method development software uses to actually predict where your peaks are going to come out. So this equation here, where C is a constant, that is used in many of these predicted method development tools to say, well, if I work at 50% organic, now I've got coelution of analytes 1 and 2, and then peak 3 is coming out prior to those analytes. You know, so we can easily see this is a bad place to work, this is a bad place to work. Maybe I want to work up here at a high percentage organic, but I've got quite long retention times. So perhaps the best place to work is down here, where I've got good separation, I've got a decent runtime, I've got quite a short runtime, and therefore I'd choose a high percentage organic in this instance, because that will give me the best separation and the best runtime, best retention times. Especially if you have a high number of samples, then this is a good choice. If you need more separation, then working up here would be better. Say you want to purify this analyte 3, then if you chose a very high percentage organic, very high percentage aqueous, then you would have a better gap between your peaks. So you can see you've got a clear relationship between your percentage organic and both the selectivity and the retention. There's other parameters that we need to think about as well when we choose our solvents. So obviously I've mentioned we're talking about reverse phase. So my solvent needs to be miscible with water. We want a low viscosity solvent. We want to make sure we don't have a lot of background. So low UV detection if I'm working with UV, potentially even lower background if we're working with mass spec. I need to make sure I have good solubilization. It needs to be chemically unreactive. And maybe sometimes this is why we don't choose methanol, because we can get some extra reaction that happens within our chromatography. Needs to be safe, so you know, environmental concerns. Obviously there's a cost factor, and purity really is something that you should pay attention to, the quality and the purity of the solvents. So acetonitrile is our most popular solvent, I would say, for LC, and that's because it ticks a lot of these boxes. You know, it works really well at low UV. We don't have much background. It's very good with different types of buffers as well. So we can use lots of additives and different types of buffer salts with acetonitrile. So that's one of the main reasons, a couple of the main reasons. In addition, and if we look at this type of plot, acetonitrile here is these black circles at the bottom. So you can see this is the acetonitrile curve. And what we've got along the x-axis is the percentage water. So we're here we've got 90% acetonitrile and 10% water, and so on as we go across the graph. Along the y-axis is our viscosity. So you can see acetonitrile is the least viscous of the solvents that we've looked at within this experiment, which means that we have nice low back pressure for our applications, because viscosity is proportional to pressure, and therefore acetonitrile is a very good choice, because we can, even with high percentage of water, we can get a low back pressure and achieve good chromatography, potentially increase the flow rate without over pressurizing our system, good for UHPLC, where you already have high flow rates as well. So this is why one of the main reasons why we like acetonitrile for as a first choice for our organic solvent. Now, I mentioned the quality of our solvents, and really it's worthwhile deciding on which type of solvent to buy based on your detection mode. What I mean by that is if you're using mass spec, there are mass spec grade solvents out there. And you can see from this experiment that we ran, looking at different quality methanols or different grade methanols, the background for an LCMS grade solvent is way lower than you'd see for a gradient grade or an HPLC grade solvent. So if you're running mass spec, you really need to use mass spec grade solvents, because if you're running a mass spec with an HPLC grade solvent and you're getting this big background peak, if that starts to interfere with any of the peaks of interest in your trace, then that's going to cause you a problem. So if you're running standard isocratic HPLC, there's HPLC grade solvent. If you're running gradient methods, then there's a gradient grade solvent. If you're running UHPLC, there's a UHPLC grade solvent. And it's not a way of marketing them, it really is important when you look at the things like background levels to use the correct grade of solvent depending on your application. There are alternative solvents to acetonitrile, of course. We spent a lot of time trying to find alternatives to acetonitrile when it was in short supply, when we had the acetonitrile shortage a few years back. But a lot of the solvents we look at for LC have different properties. And this was described quite a long time ago and probably best represented by Snyder in this 1974 publication. So he was looking at the different properties of solvents that we thought were good for LC, or potentially looking at lots of different solvents and then choosing which ones would be most suitable. And you can see within this triangle, they all have different properties. And the reason perhaps we want to switch between one solvent and another solvent is because of those properties, because that will have an impact on the selectivity within our separation. So picking solvents that are as far away from each other in this triangle as possible would really be good for your method development. Now, there's reasons we can't pick solvents from these groups, often because of they don't fit the criteria we just looked at. So they're not soluble in water, or they're hazardous, things like that. But we've got good solvents in these three categories that are very good for LC. So we've got acetonitrile, methanol, and not as often used, and probably many of you will say not that nice to human health, is THF as well. But they do give us different properties and therefore different advantages when we want to move our peaks around. So definitely for method development. But if you're trying to substitute one for another, you'll see that isn't always the easiest substitution to do. So each of these solvents have different solvent strength based on their polarity. So the low polarity solvents at the top here have a strong solvent strength, and water at the bottom here, which is our highest polarity solvent, has a weak solvent strength within reverse phase HPLC. So if we just pull out three of these solvents, and unsurprisingly they are ones I've just mentioned. So we've got methanol here, which is a stronger solvent than water, and we've got acetonitrile, which is stronger than methanol, and then right up here we've got THF. So that is a pretty strong solvent when it comes to HPLC. And if we want to start substituting our different organic solvents, we need to consider the fact that they have different strengths. So for example, here we have 50-50 mix of acetonitrile water, and you can see the retention time of my 3 peaks. If I just substitute my acetonitrile with methanol, then my retention times shift. So the K value changes, and actually there's some change in selectivity as well, alpha. So methanol is a weaker solvent. That means I've got a longer retention time. And you can see here the difference that you get even using the same percentage, methanol versus acetonitrile. THF is a stronger solvent. So as expected, because it's a stronger solvent, everything comes out earlier. I've got shorter K values, shorter retention times, because this is a strong solvent. And we can look at these solvent nomograms to say, well, actually, if we want to have the same chromatography, the same retention, then we need to match up the solvent strengths. So here, if I want the same retention as my acetonitrile method up here, I can choose 61% methanol or 37% THF, and I'll get pretty much the same chromatography dependent on if there is some sort of additional selectivity effects. So if these are all neutral compounds, this is what will happen. What tends to happen in reality is there'll be some other interactions because of those different solvent properties that then moves our peaks slightly. But if you're just trying to match up the solvent strength, then this is the best way to do it, looking at these nomograms and making sure that for weaker solvents you use a higher percentage of the organic modifier, and for stronger solvents, of course, you can use less, and that will achieve the same, approximately the same retention. Now, as I mentioned, that would be great, but we also have these other properties of the solvents. So sometimes, even if you are using the same strength of solvent, you will see a change in selectivity. So here we've matched up the solvent strength approximately, and with acetonitrile we get coelution of peaks 4 and 5, but when we use methanol we get a nice separation. And this can be really powerful for your method development, because now there's other properties that solvent has that is helping change selectivity and to pull my peaks apart. Doesn't help you if you can't get hold of acetonitrile and you want to give exactly the same method. And this is the problem we came across when we were substituting acetonitrile with other organic modifiers, because the selectivity plays a role, especially if you've got ionizable compounds. This demonstrates with acetonitrile again, our favourite solvent, how changing the percentage of acetonitrile can both change the retention and the alpha, so the selectivity. And you can see as we go down the screen here that increasing the aqueous component, so increasing the weak solvent in this case, means we get longer retention times. You can see that. You can see these coming across the screen. And you can see some changes in the peak spacing. The peak selectivity is changed as well. So I would suggest that if you're going to use this as your experiment to find the right concentration of acetonitrile water, don't just change it by 10%. Do make sure there's a significant change in the percentage, 20, 30% ideally. We'll really start to see if this is a good way to go. And you've seen from those early graphs that actually you only need to look at 2 different percentages, a high one and a low one, to draw your straight lines for each peak, and then you can pretty much pick the right percentage organic to choose to work out for the best separation. So because they're linear, you can pick 2 points quite wide apart. Your third point would be the one to prove that that's the correct percentage organic to work at. And here you can see this 45 to 55 ratio gives us the best separation. It's in between these two percentages, and you've got a nice separation of peaks 4 and 5 actually achieved with 55% aqueous. Whereas if you start then going up to 60%, then they're starting to coalute. You can see that peak 4 is moving into peak 5. We use this as one of our screening tools, really. We look at different column selectivities, but in addition to that, we look at different organic modifiers, so organic solvents. And, you know, acetonitrile and methanol, they're our favourites, so we will choose to look at both of those solvents when we're doing our method development screening to make sure that we're using as much of that selectivity space as possible. We're really exploiting that alpha value in the resolution equation to try and pull these peaks apart. So you can see, especially here, we've got coelution of peaks 8 and 9 within this box in acetonitrile, but if we go to methanol, peak 8 is much better retained, peak 9 is sat here alone. So you get very significant changes for some compounds by changing the type of organic solvent that you're working with. Now, we can get even more complex and look at 3 solvents. So we can have our methanol, our acetonitrile, and our THF. And I would say it's best to work with just that mixture initially. But if you don't get what you're trying to achieve with a single solvent, then you can start to blend together more than one solvent to hopefully get your separation. If all else fails, potentially you could mix them all together, but the more complexity you have in your mobile phase, the more problems that could potentially occur, especially if you want to transfer this to a QC lab or a different lab. The more complex the mobile phase, the more challenging it will be to transfer. So keep it as simple as possible. Not always the case. You can't always get away with just one organic solvent. In this example here, for example, we had 3 attempts at separating our 9-component mix. So here we've maintained the same solvent strength in each case. That's why you can see there's a different percentage organic in each application. And unfortunately, we've got coelution of peak pairs in every run. So that was unfortunately not a nice, straightforward method developed. The best thing to then do is to try and blend some of these solvents. And as we like methanol and acetonitrile, we'd probably look here. But, you know, in this case, because they had the same peak pairs coeluting, it's better to choose the third organic solvent, THF, because this had a different coeluting pair. And nicely, if we mix acetonitrile and THF and water in this ternary mix, we get a good separation of all of the components in our mixture. So ideally, I'd like to run this, but because they've got the same coeluting pairs, it made more sense to use THF in this case. Here's another example. This actually does mix methanol and acetonitrile. You can see you've got different coeluting peak pairs in the top 2 chromatograms, but when you blend together methanol, acetonitrile and water, you get a good separation of all of the analytes in our mixture. So that's another thing to consider, really. If you're struggling with just one solvent, then don't be afraid to mix in another one. You might, in your method development, want to try that it's easier, obviously, at that stage than sort of further down the line. So the final thing that is affected by our mobile phase in that resolution equation is the efficiency. I haven't really touched on this, but you can see, for example, here when we've matched the same solvent strength with acetonitrile and methanol, run the same mixture of analytes down the column. With our acetonitrile separation, the plate number, the N number, the efficiency of our final peak in this separation is higher with acetonitrile than it is with methanol. So again, you get differences in that efficiency term, so the peak sharpness, when you choose different solvents. Potentially this is because of the reduced viscosity, it's got better mass transfer in the system, that's why you're seeing a higher efficiency. But you'll see different properties when you move from acetonitrile to THF to methanol, for example. So they're all having pretty significant impact on this resolution equation that we showed at the beginning. So hopefully that shows you how important your mobile phase is and your choice of organic solvent. We're now just going to briefly look at gradients. And for those of you not familiar with gradients, most of the applications I've shown you have just been a percentage of acetonitrile plus water. So you have a consistent mobile phase through the whole run. That's called an isocratic method. When you change the percentage of the organic solvent normally, especially for reverse phase, so when you change the percentage B, that's called a gradient method. And you can see here some examples of what that's like. So isocratic, we have consistent mobile phase through the duration of the run. And for a gradient, we increase the percentage B. There are big advantages to working with gradients. Mostly if you have a different hydrophobicity range or a different polarity range for your analytes in the sample, then a gradient is a really good way to separate them all within a decent time frame. Also, the peak widths of all of your peaks in this separation should be about the same. And that means that we don't get these short blobby peaks at the end of our run that we see in isocratic. We're pushing the back of the peak in. That means it's getting taller, it's getting narrower, getting sharper, and therefore we get better signal to noise as well. So there's a lot of key advantages to working with a gradient method. Now, gradients are not just the kind of 5 to 95 in 10 minutes. We have a whole cycle that we need to think about when we're running a gradient. Obviously, we talk about this 5 to 95 in 10 minutes, but we need to also consider an isocratic hold at the end of the gradient, a fast ramp back down to our starting conditions, and then this nice section here of post time. And what that section does is it gets everything back to the starting conditions. And what we need to be wary of in our gradient methods is that we make sure that post time is long enough, because we need all of our conditions to be back to the start before we have our next injection, our next 5 to 95. And the length of that does depend on what you're doing, of course. Depends on the gradient range. So 5 to 95 or 50 to 70 is going to need a different post time. But really, as a rule of thumb, I would say at least 10 to 20 column volumes would be important to have in between each of your gradient methods. And that's a reverse phase. If you've got ion pairs in there, or if you're running Hillock, then it should be much longer than that. I don't have time to go into sort of all the details there, but make sure that you're always starting at the bottom of this gradient slope, because if you start your next injection before everything's fully equilibrated back to those starting conditions, then you're going to get a lot of inconsistent chromatography. So how do I know whether I should run a gradient or whether that isocratic method is fine? And there's a nice simple trick to know whether a gradient is better than an isocratic. What it does involve is one scouting gradient run. So if you've got a mixture of analytes, you don't know sort of what the best method is going to be, then if you run a nice wide, so broad scouting gradient to start with, and look at where the peaks elute within that gradient, if there is more than a 25% change in percentage B required for all of the peaks to elute, then a gradient method is better than an isocratic method. And there's lots of words on this slide, but it's much easier if I show you in a real example how this works. So here I've done my gradient survey, my scouting gradient. So I've run 0 to 100% B over 25 minutes. And all of my peaks in my sample have come out in a big bunch in the middle. So you can see there's not a very wide window where these peaks all elute, which is suggesting they've all got a very similar types of properties, really, types of polarity. So what I want to do is look at where the first peak and the last peak elute and how big a difference there is in the percentage B between that first peak and that last peak. You can see here it's actually clearly smaller than 25%. So this is less than 25%, and that suggests that actually we could run this isocratically and get a better separation. What percentage B do we need? Well, we can use this retention time of peak 1. We can use this nice little equation, which is minus 2.5 and then times by the T0 in minutes. And that gives us 10.7 minutes. We then read off the percentage organic at 10.7 minutes, which is 47%, and that's our percentage B that we want to use isocratically to get a good separation. If we run that, you can see here nicely we have a really good separation within 10 minutes using 47% B. And we can optimize this further, increase the flow rate, use a shorter column if we want to speed this up. But it shows you can quite readily do an isocratic method, not have to worry about any of those post times with this set of analytes. If we look at the other extreme, so here now we've done our 0 to 100% B over 20 minutes in this case, and we've got a broader spread of peaks. The peaks are eluting in a wider time frame. If we look at the first and last peak, you can see it's more than 25% change in B, which means a gradient would be a better choice for this set of analytes. But obviously we haven't really optimized this gradient. We've got a lot of dead time at the start. So what gradient range should we choose? And again, we use a very similar approach. So we look at the first peak, we take away 2.5 and we times it by the T0. We look at the last peak, take away 2.5, times it by the T0. And then we read off what percentage B those equate to. So this is suggesting now that actually we should run not 0 to 100% B, but 54 to 87% B to achieve a good separation of these analytes. What does that look like? Well, nicely, we've got rid of all that dead time at the beginning. Our peaks are coming out within 15 minutes. I would say there's still quite a lot of dead time between these peaks. So now we can look to optimize that method further. We can use a shorter column, use a smaller particle size, increase the flow rate. But it gives you a good indication that the gradient is a better choice than an isocratic method for this type of analyte mix. So hopefully that gives you an idea of whether to choose isocratic or gradients for your analytes. So the final section I just wanted to mention was buffers, and really looking at pHs because they're very important, and that's what our buffer is there for. It's there to keep a consistent pH. When we change the pH, we again change those factors in the resolution equation. So we change selectivity and retention, and that has also a really significant impact on the method robustness or the method ruggedness. If we go back to our chemistry days at school, you think about ionization and this sort of acid base. We're working with reverse phase, and the best state for an analyte to be in reverse phase is its most hydrophobic phase, which means that if it's ionized, if it's positively or negatively charged, we're not going to get good retention. We're not going to get good interaction with our hydrophobic C18 column. So it's best for us to work with the analytes in their non-charged form. If we can't do that, then it's best that they're just in one form, not in this equilibrium that's very close to the pKa, for example. Because in theory, if you've got some part of your analyte, some of your analytes are charged, some are not charged, then you will have two peaks. In reality, what happens is this is in equilibrium, so you don't get two peaks, you get a large, broad, wide, often tailed peak. So for an acid, you look at the red trace here, we're looking at pH along the x-axis and the retention time or retention factor along the y-axis. So if we look at our acid, we get good retention at low pH, but as we increase the pH, we ionize that acid, it becomes more polar, less hydrophobic, and therefore we get poor retention. If you've got a neutral compound, pretty much stable, the retention time across the pH range. And if you've got a base, you've got the opposite of an acid, so you have poor retention at low pH because the base is ionized, and you get much better retention at high pH because now you have a neutral compound, and that's better for reverse phase. So it would be best to work in these robust or rugged zones, not on these steep slopes where very small changes in pH can lead to very significant changes in retention. And although these are nice, big, robust zones, you've got very poor retention of bases at low pH and very poor retention of acids at high pH. So again, best place to work is up here on these nice plateaus because you can get away with slight changes in pH without losing retention. Worst place to work is on these curves, on these significantly steep slopes. And again, that's just shown here with an acid, a base and a neutral. And you can also see that changing the pH will change the elution order, so the selectivity, that alpha value. So at pH 2.5, my retention order is base is poorly retained, got coelution of my acid and my neutral. Go up to pH 5, I've got good separation, not too bad retention of everything, acid's not greatly retained. And then up at pH 7, my acid comes out first, my neutral second, and you can see we're starting to be on that steep slope of the base. So here, any slight errors in making up mobile phase will lead to big shifts in the retention time of your basic compound. You can look at this in a model as well. So I mentioned before, we use a lot of these theories in our method development software. And this is a resolution map from ChromeSword. So this is showing you along the x-axis pH and along the y-axis resolution. So you can see as we change pH, there are big changes in the resolution of the critical pair we have in our chromatogram, in our analyte mix. Really bad places to work are down here because I've got co-eluting peak pairs. This would be a pretty good place to work because I've got the highest possible resolution, but you see how sharp this is. Very slight change or error in the way I've made up my mobile phase will lead to a very big shift in the resolution. So maybe better to work around this area where you've got a bit more leeway if there is an error in the pH. Would be nice if it was a proper plateau, but these things tend to be not quite as nice in real life. So it's worth looking at different pHs. Obviously you have to work with different buffer salts when you're analysing when you're trying to achieve different pHs. So always be wary of the solubility of said buffers and your application detection mode, because some buffers are not going to be LC-MS compatible. You can see here with this mixture of two analytes, increasing the pH actually separates out what were two co-eluting peaks into two well separated, but ideally not really that great efficiency peaks. So you might be better off working sort of around pH 7 than going all the way up to pH 10 in this case. And you can see that because of the nature of them, these are bases, you are getting longer retention times when you've got higher pH. Word of warning, you can see here the pH for two runs. So this is the same test mix, same column, same mobile phase. The only difference is two people made up the mobile phase and there is a slight error in the pH. So I've got 0.1 change in pH units and it's resulted in a complete loss of my baseline resolution for this critical peak pair. So it probably means I'm working near the the pKa of one of these analytes. I'm working on one of those knife edges within the resolution map, and even a small error that, you know, if your pH meter isn't fully calibrated, or if it's within experimental error often in labs to have that 0.1 pH unit difference, and I've completely failed my system suitability because I haven't got the right pH. And it's not just this one example. We've got numerous examples where you can really lose resolution because of a slight difference in the pH. So do look at the robustness of your method. Do look at 0.02. Do look outside the pH range. Is your method robust enough if you have a slight error in pH? In this case, it's not. Now we've got horrible co-elution of these peaks with just 0.1 pH unit difference. So there's lots of buffers we can use to achieve different pHs. And when you're doing method development, maybe you want to do some blends of acetates and phosphates so you can cover the whole pH range. Choice of buffer should be, again, related to what pH you're working at or want to work at and what detection method you have. So make sure it is compatible with your detection method. Always work within 1 plus or minus 1 pH unit of the buffer pKa. That's when it's actually going to be buffering. I've seen lots of methods where there are stated buffers, but actually if they're not within that plus or minus 1, it's not actually doing its job. How much do I need? Well, as little as possible, really, in terms of the buffer. It only needs to buffer the analyte, the column, and the sample. So if you're using a new generation column, if you are matching your sample diluent to your mobile phase, then you really don't need much buffer in terms of the ionic strength, because it doesn't have that much to buffer. This is looking at a C18 column and looking at different ionic strengths of the same potassium phosphate, pH 5.5. So we've maintained the same pH. All we're doing is looking at changing the ionic strength. You can see as I go up the screen here, I've got an increased ionic strength. Now, at 1 millimolar, I don't have a high enough buffering capacity. But I only need to go here to 5 millimolar to see pretty decent peak shape. I'm in peak 4 here, got a bit of fronting, but it's so much better than 1 millimolar. And going up to 15 millimolar, well, now I've improved that peak 4, but this critical pair here is starting to join together. So potentially 10 millimolar would be enough to get a good separation, a good buffering capacity in this instance. And I've seen a lot more methods that use much higher ionic strength. So use as little as possible. That's going to be of benefit to you. It does depend on your column. So if you look here, now we've moved to a cyano column, and you can see a completely different picture, even with the same type of salt, the same pH, and the same analytes. So here I actually need to do a bit more optimization with my buffer, because I've got okay buffering capacity here. I've got, I would say, good, if not better, buffering capacity at 5 millimolar, but I've got big significant changes in the selectivity. And some of that is related to competition for ionic sites on the surface. Some of it's related to the fact I've got this strong dipole. So there's other factors that play a role when I'm working with different ionic strengths. And it doesn't just affect reverse phase. So if you run any Hillock methods, I apologise, this is the other way up. So now I've got the low molarity buffer at the top and the high at the bottom. But it's just showing you that for other modes of chromatography like Hillock, you do also need to really think about the ionic strength. Here, peak 3 loses retention as I increase the ionic strength. But peak 2 increases in retention. And that's because I'm working with a different mode of chromatography. And you can see it quite clearly here from the crossover of these lines. But I just wanted to really get you thinking that whatever mode of chromatography you're running, you should build in ionic strength as one of the parameters to look at during your method development. Because a lot of the time we've got too much buffer in there, we don't need all that buffer, and you're going to get better results if you've got slightly lower buffer concentrations. But for some instances you need more, so it's worth looking at. Final couple of slides are just on some housekeeping. I've said most of this. Make sure you are using a buffer. Ideally work 2 pH units away from the pKa, and other things affect pH, like the temperature, like what solvent you're using with it. So do be aware of those factors. Also be aware of the solubility of buffers. They're going to be different in different organic solvents. So again, I've got my 3 favourite solvents here, acetonitrile, methanol and THF, and you will get different solubilities of different buffer salts in each of these. So make sure you're not getting any precipitation, especially when you're online mixing, because that can be a major problem. If you are concerned, then do it offline. Check in an aliquot, check that you're not getting any precipitation when you mix A and B by putting them in vials and then mixing them together, ideally in a cold, in a fridge, for example. You'll soon see if you've got any buffer crystals forming. Not going to go through the tips and tricks because I presented on troubleshooting last year. So there is a recorded webinar on vwr.com with some tips and tricks about how best practice for making up correct mobile phases. So do check that out. And finally, I wanted to say we have lots and lots of resources. So please do visit vwr.com/chromatography or vwr.com/chemicals for our chromatography sections and our solvent sections. Lots of great resources like white papers, knowledge notes, this really good book that we wrote in conjunction with John Dolan about buffer selection, and some tips and tricks there. And if you have any questions, please do contact us. We've got a fantastic tech support team. Use that chromesupport@avantalsciences.com email address. This is Cassandra, who's been answering your questions as I've been talking. So please do use that great team of experts as well. And thank you very much.